Today let us start our fifth unit. In the fifth unit we will study about superposition of two harmonic waves, and the first topic is standing or stationary waves in a string. Actually there are three cases. One is fixed, that is fixed ends, that is both the ends of the string will be fixed. Secondly, one end will be fixed and other one will be free, and thirdly both the ends of the string will be free. So let us start this topic. First of all, let us know something about standing wave or stationary wave, that is how we obtain standing waves or how standing waves are formed. So standing or stationary wave is the resultant wave formed by means of superposition of two identical progressive waves traveling through medium along the same path but in opposite directions. Identical progressive wave means waves having same amplitude, same time period and same wavelength. That is two waves with these characteristics, that is two identical waves propagating through a medium along the same path but in exactly opposite direction, then their superimposition will give us standing or stationary waves. So in order to have standing waves, we need two identical waves propagating along the same path but in opposite direction. So why that superimposed wave is known as standing waves, we will discuss later on. But firstly, let us discuss the formation of standing waves in a string as an example. Here we will consider the case that both the ends of the string will be fixed. So let us consider a string of length L fixed very rigidly at x equal to 0 and x equal to L. That is, the end points are here at x equal to 0 and at x equal to L. So we know that when the string is set to vibration by any means, say by means of plucking, we have set the string to vibrate. We know transverse waves will generate and begin to travel along the length of the string. So now imagine that transverse wave is propagating through the string towards the end points. So since the string is fixed at the two ends, two waves will be reflected back from the supports and will interfere with each other. So as a result, we will get standing waves. We know that the differential equation for traveling wave motion is given by this expression. Here v is the velocity of the transverse waves generated in the string, and if we solve this expression, we obtain two traveling wave. One is propagating along positive x direction and other is propagating along negative x direction. So due to superposition of these two waves, we will obtain standing wave, and the resultant wave or superimposed wave is given by this expression, that is yxt equal to y1 plus y2, which is equal to a1 e to the power I omega t minus kx plus a2 e to the power I omega t plus kx. So since this wave, superimposed wave, is generated in the string, so for this expression the general boundary conditions must be applicable. That is, the general boundary conditions will also satisfy by this expression. So since the string is fixed at the end points, that is at x equal to 0 and at x equal to L, the two end points will have no y displacement. They will be always fixed. So as a result, we obtained two boundary condition at x equal to 0, y equal to 0, and at x equal to L, y equal to 0 for all values of time. These two boundary conditions will be satisfied by the resultant expression for standing wave. So if we firstly apply the first boundary condition, that is for x equal to 0, y equal to 0, then we will get y equal to 0, and here a1 e to the power I omega t, since x is 0, so this in this term we will have only a1 e to the power I omega t. Similarly here for this term we will get a2 I omega t, and e to the power I omega t is non-zero, cannot be 0, so for an existing wave, therefore a1 plus a2 must be equal to 0, which implies a1 equal to minus a2. So this means that the amplitudes of the two waves are equal in magnitude, but their sign is opposite. And let us consider that a1 equal to minus a2 equal to a, their magnitudes are equal to a. So if we now apply the second boundary condition, that is for x equal to L, y equal to 0, in the general expression for standing wave, then we will get what? Here 0 and a1 e to the power I omega t minus k L plus a2 e to the power I omega t plus kl. So if we apply a1 and a2 equal to a, that is here a and a2 will be minus a, then we get, after application of this boundary condition, we will get y equal to 0, a e to the power I omega t minus kl minus a e to the power I omega t plus kl. So after some mathematical simplification, we will get e to the power I kl minus e to the power minus I kl equal to 0. So for this expression, we have a standard formula. So e to the power I theta minus e to the power minus I theta equal to 2i sin theta. So we will get 2i sin kl equal to 0, which in turn lead us to have kl equal to n pi. Here n is 1, 2, 3, etc. That is non-zero integers. Here n equal to 0 value is not acceptable. This will lead us to an undefined wave. So from this relation, we will get k equal to n pi by L. And again, since we know k equal to 2 pi by lambda, or say lambda equal to v by or k equal to omega by v, and omega equal to 2 pi nu by v. So from these relations we will be able to find out different physical quantities such as wave number, wavelength, angular frequency, or frequency of the standing wave generated in the string in terms of length of the string. So all these quantities are dependent on the length of the string. Further, for different values of n, we will obtain different values of k, lambda, frequency, etc. So actually each value of n will correspond to a different standing wave pattern, and the patterns are alternatively called modes of vibration on the string. And since we get different wavelength and frequency for different n values, here we have written, means we have used the subscript n for wavelength equal to 2L by n, and corresponding frequency nu n equal to nv by 2l, and these two expression corresponds wavelength and frequency of the standing wave generated in the string in nth mode of vibration. So now let us visualize the standing wave pattern generated in the string in different mode of vibration. So firstly, let us consider the n equal to 1 case. For n equal to 1, from this formula we will get lambda 1 equal to 2l. That is, the wavelength in this mode of vibration will be twice the length of the string. So lambda 1 equal to 2l, twice the length of the string. And on the other hand, from this expression, that is l equal to lambda 1 by 2, we can say that we can accommodate half of the wavelength in the string. That is, half of the wavelength fits within entire length of the string. Here the corresponding frequency is v by 2l. So the pattern of vibration of the string in this mode is given by this expression. This is the these two, this one and this one, are the possible mode of vibration for n equal to 1, according to this formula, and also satisfying the general boundary condition, that is at x equal to 0, y equal to 0, and at x equal to l, y equal to 0. So this mode of vibration is known as fundamental or first harmonic mode. Now for the n equal to 2 case, we observe that lambda 2 equal to 2l by 2, that is equal to l. This means that the wavelength of the standing wave generated in the string is equal to the length of the string. That is, we can accommodate one complete wave, one complete cycle of the wave in the string. But here one thing we observe, that lambda 2 is equal to lambda 1 by 2, that is half of the fundamental vibration. Wavelength is half of the wavelength of fundamental harmonic. So the corresponding frequency in this regard is nu 2 is equal to twice nu 1, that is 2 times of the fundamental frequency. So the possible pattern of the standing wave for n equal to 2 case is this one and this one. So the string will vibrate in this way. This mode of vibration is known as second harmonic mode. Similarly, we will get the third harmonic mode for n equal to 3 case, and here lambda 3 will be twice l by 3, and in this case the within entire length of the string we will be able to find 3 by 2 times of the total wavelength of the standing wave, and the corresponding frequency will be 3 times the frequency of fundamental frequency. So from this pattern we observe that the stationary waves generated in a string with 2n fixed, only some fixed frequencies are produced. So here you see we have nu 1, that is v by 2l, then other possible frequency is 2 nu 1, then next one is 3 nu 1, like this. So only some fixed frequencies are produced, and these frequencies are called characteristic frequencies or eigenfrequencies. There means no other frequencies are possible in this case. So these are called characteristic frequencies or eigenfrequencies. Now let us discuss the position of nodes and antinodes, because here we see that in the patterns, standing wave patterns, we observe some zero crossing. That is, the wave is means the wave has zero crossing here, here, similarly here. That is, amplitude of the resultant wave is 0, and at some other points, say here and here, amplitude is maximum. So the points where amplitude is minimum is known as node, and the corresponding point where the amplitudes are maximum are known as antinodes. So let us discuss the position of nodes and antinodes in this regard. But before discussing position of nodes and antinodes, let us discuss about the resultant wave in terms of different parameters. For example, amplitude, angular frequency, and k, because we know now these parameters. So the resultant wave is given by yxt equal to a e to the power I omega t into e to the power minus ikx minus e to the power ikx. So here a1 a2 is a with one is opposite sign, but actually we should use the subscript, that is here a e to the power I omega n t, and here e to the power minus I k n x minus e to the power I k n x. If here also we should need n, so you correct this one. So yn means we are discussing the standing wave, general expression for standing wave in nth mode. So you consider that there is the subscript n. So if we take minus common from this bracketed term, then we will get a minus a e to the power I omega t into e to the power ikx minus e to the power minus ikx. And as we know, e to the power I theta minus e to the power minus I theta equal to 2i sin theta. So we get minus a e to the power I omega t 2i sin kx. So here we have the terms like 2a, this is 2 and a, 2a, e to the power I omega t, and then minus is here, minus I, and then sin kx. So this is the phase term, and these are the terms with amplitude. So although we observe that the amplitude contains an imaginary number, but actually this number or this term may be absorbed within the phase term. So how this can be absorbed in the phase term, let us see. So this is 2a e to the power I omega t. So minus I may be expressed in this way: cos pi by 2 minus I sin pi by 2. Here cos pi by 2 is 0, minus I sin pi by 2 is 1. So 0 minus I, so means minus I, and sin kx is there. Again we know cos theta minus I sin theta equal to e to the power minus I theta. So this expression, from this expression, means from the bracketed term, we will get e to the power minus I pi by 2. So combining these two terms, we will get e to the power I omega t minus pi by 2. So as a result, we obtain the general expression for standard wave in nth mode is equal to 2a sine n pi by L into x e to the power I omega t minus pi by 2. Here minus I, this term is absorbed as phase or within the phase term. So here we observe that the amplitude of the standing wave is 2a sine n pi by Lx, that is the amplitude varies sinusoidally. For sine n pi by Lx equal to 0, we will get 0 amplitude, that is the wave will vanish, and for this is equal to 1, we will get the maximum value of the standing wave, the value of the amplitude. So from this point, means observing this amplitude, we will be able to find out actually the position of nodes and antinodes. But before discussing the position of nodes and antinodes, let us obtain another form of this expression for standing wave, and that is this form can be obtained directly from this expression. Here 2a minus I is there, 2a minus I, and sine omega n x by v means actually since k is equal to omega by v, here we have used the subscript n, so omega n by vx, this is common term. So 2a minus I is here, 2a minus I is here, and e to the power I omega t is expressed like this. E to the power I theta is cos theta plus I sin theta. So here we have cos omega n t plus I sin omega n t, and with this 2i common term, we will get 2a minus I cos omega n t plus 2a sin omega t. So here let us consider that 2a into minus I equal to an, and 2a equal to bn, then the resultant wave may be expressed like this also, an cos omega n t plus bn sin omega n t, then sin omega n x by L. So this is in terms of omega n. Here an and bn satisfies this relation. So an square plus bn square whole to the power half means root over an square plus bn square will be equal to 2a, and 2a is the amplitude of the resultant wave, maximum amplitude of the resultant wave. So here you see an is what, 2a minus I, so square of this is 4a square, so sorry, minus 4a square, and minus 1 square is minus 1, so minus 4a square, and here it is 2a square, so means 4a square, 4a square. So if we add and then take root over, we will get 2a, means 4a square, root over 4a square. So we will obtain this form as the alternate form for resultant wave. Now let us discuss the position of nodes and antinodes. So we know that general expression for standing wave in a string is given by yn xt equal to twice a sin n pi by Lx e to the power I omega t minus pi by 2. So Here amplitude term, that is 2a sine n pi by Lx, is a function of x and varies sinusoidally and has maximum value 2a and minimum value 0. So the points, that is the x values for which yn equal to 0, that is the points which never moves are called nodes, and for nodes sin n pi by L into x must be equal to 0, and this is possible for sin m pi, where m is an integer containing 0. So what happens for sin n pi by Lx equal to 0, n pi by Lx must be equal to m pi, and using this subscript m, xm is ml by n. So equating this with this one, so we will get xm equal to ml by n. Here n takes values from 1 to 3 etc. It is non-zero integer, but here m takes values like 0 to 1 2 3 etc. So this xm values gives us the positions where nodes occur for nth mode of vibration. Nodes occur for nth mode of vibration. So for example, for fundamental mode, that is for n equal to 1, xm, possible values of xm are 0 and L. That is for m equal to 0, we will get xm equal to 0, and for m equal to 1, we will get xm equal to L. Here n equal to 1. For n equal to 1, xm takes only 2 values, because for m equal to 2, you see, for m equal to 2, the position will be, xm will be 2L. So 2L point is beyond the string. That's it, because our string is length of the string is L only. So there is no any point within the string at x equal to 2L. So similarly for the second harmonic mode, that is for n equal to 2, here n is 2. Now for different values of m, we will get some positions. So for m equal to 0, we have xm equal to 0. For m equal to 1, this is 1, so L by 2, xm will be L by 2, and for m equal to 2, xm will be L. So we will have some positions 0, L by 2, L, where y displacement is 0. So here if we use m equal to 3, then 3 by 2L, this is not a point within the string. So similarly for n equal to 3, here n is 3, and for m equal to 0, we will get a point 0 for xm, then for 1 L by 3, and for 2 2L by 3, and finally L. So let us visualize this point. For n equal to 1, there are 2 points at 0 and L where the y displacement is 0. So you just see the fundamental mode of vibration. Here at x equal to 0 and x equal to L, y displacement is 0. Now for the second mode of vibration, there are 3 points, x equal to 0, x equal to L by 2, and x equal to L, where y displacement is 0. So you see there is at x equal to 0, at x equal to L, and in between them. So here we can easily verify the position of node at x equal to 0, x equal to L by 2, and at x equal to L. So similarly for the third harmonic mode, third harmonic mode, that is for n equal to 3, we have 4 points where y displacement is 0. At x equal to 0, L by 3, 2L by 3, and at x equal to L. You see here x equal to 0, this point is L by 3, x equal to L by 3, and this will be 2L by 3, and this is x equal to L. So in this way we can obtain the position of nodes for the standing wave. Now there are some points where y displacement is maximum, that is amplitude is maximum, and those points are known as antinodes. And for antinodes, the amplitude maximum, that is sin n pi by Lx equal to 1, which is possible only if n pi by Lx takes these values 2m plus 1 pi by 2 for all values of m, integer values including 0. So in this regard, the position where amplitude become maximum are 2m plus 1 by 2n into L. So these are the positions of antinodes for nth mode. So for first mode, that is for fundamental mode, n equal to 1, xm equal to L by 2. So here if we use n equal to 1 and m equal to, possibilities are 0 firstly. So for m equal to 0, we will get L, and here 2 is there, so L by 2. If we use m equal to 1, that is 2 plus 1, 3 by 2. 3 by 2 L is not a point within the string. So there is only one point where amplitude becomes maximum, and you can easily verify from this figure. There is only one point where amplitude becomes maximum, and that is the x equal to L by 2, that is middle of the string. Similarly, for the n equal to 2 and n equal to 3 case, we will get here 2 points at L by 4 and 3L by 4 for the second mode of vibration where amplitude become maximum. You see L by 4 and 3L by 4. You see for the second harmonic mode, there is a point, that is L by 4. This is 1 by 4 of the wavelength. So L by 4 and 3L by 4. At this point and at this point, amplitudes are becoming maximum. So similarly, for n equal to 3, we will get 3 points where amplitudes becomes maximum, and these points are known as antinodes. So in this way, we can obtain the standing wave patterns generated within a string. And now let us discuss why this pattern or this wave are known as standing wave. Here we have seen that when the two waves of same amplitude and frequency travel in a medium in opposite directions with the same velocity, then due to superimposition of the two waves, there are some points of the medium which have no displacements. That is, we call them nodes, and there are some points which vibrate with maximum amplitudes, which are called antinodes. The resultant wave remains confined in the region in which they are produced and is non-progressive in character. Thus, these waves are called standing or stationary waves. So here we observe that the wave is confined. The wave is confined within the two endpoints or within the two rigid support. So since it is confined, So that's why it is called standing or stationary wave. And there are some fixed points. Say this point is always at this point, this is not moving, and similarly this point will always vibrates at which amplitude is maximum. So this wave is generally non-progressive in nature. So that's why these waves are known as stationary or standing waves. Thank you.